Okay, hello everyone. I'm very happy to be here with you. And once again, thank you very much for your amazing contribution to our competition of Landslide4sense. In the previous session, my name is Omid Ghorbanzadeh. I'm also from IARAI. In the group of AI for remote sensing, leading by Professor Dr. Petram Hamisi. About this competition, as in previous session, Professor Kumar mentioned about the challenges of state-of-the-art AI that we have for remote sensing applications. We also have the same and even some more, such as class imbalance and the lack of label and the problem of transferability for remote sensing applications. So these are the challenge that motivated us to launch such a competition for detecting landslides from Earth observation data. So what we provide in this competition, all were freely available open access data from Sentinel-2. So we have two bands from Sentinel-2 as our optical data, and also the slope and digital elevation model, the elevation information from Alus Pulsar satellite data. So in overall, we have 14 layers of 14 bands that we are going to detect landslides from them. Again, what we provide for just the training data, and the data collected globally from very different geographical location, very different topographic information, and also land cover information and characteristics to increase the diversity in our training data. So we had three sources of data: training, validation, and test. And I can say all are different to focus also on the challenge of the transferability of the AI solution for landslide detection. For the training, the data was from higher Himalayas, south of India, from Taiwan and Japan. And the triggers of landslides are also different in our training data, also validation and test. Some are happen because of earthquakes, some because of rainfall, and for the case of Japan, it was the mix of both. So the challenge of class balance, that as you can see, how much, for example, we have the class of landslides for the case of Japan, and comparing it with in Kodagu district in India, you can see the imbalance that is really obvious for the class of landslide and non-landslide. This is also the same for higher Himalayas in the case of Taiwan. So these four case study areas just used for producing the training data. They didn't use in validation and also test. So this is how it looks like our data, 14 bands. Until 12, they are optical layers from Sentinel-2. They are in different spatial resolutions from 10 meters to 60 meters. but like for make it more simple, we like resize all of them to 10. And like last two ones, like slope information and digital elevation model, plus with labels, that we also provide labels for training data, but not for validation and test. So the ranking of competition for the competitors was just like F1 score, but we also provide them with recall and precision to get better understanding about the performance of their model. But the ranking was only based on F1 score. So we provide the classic unit as a baseline model to the competitors, and provide the code and the structure and the data also in our GitHub and in our website. We were really active in competition forum. So very impressive. We got received 7,775 submissions during validation phase, and at the end we asked competitors to submit an abstract to explain their methodology and including the name of team that they are working on the work. So at the end we received 29 submissions, and during the test leaderboard, when it was open, we got 219 submissions, and we put because we put limitation of maximum number they could to submit was just 10. So we had like unique registrations from 37 countries all over the world, from Canada to Australia, almost everywhere. And the most unique users that contribute in the competition was from China with 134, following from Hong Kong, US, Germany, Canada, and Austria. So I was really generous for the prices. As you can see, like 5,000 euros for the first team ranked as the first, and also we had one more like special prizes for creative and innovative solutions in AI for landslide detection. So based on F1 score, the team of Kingdrone, let's come here, from School of Remote Sensing and Information Engineering from Wuhan University of China, they ranked as the first based on their F score during the test phase, and the second team is SIG from Xidian Artificial Intelligence Institute, China, and the third team, Tanmlh, from DLR and Technical University of Munich. So these are our three teams that from first to the third that ranked based on their landslide detection and their F score results. As I said already, we also had a special prize for creative and innovative solutions that was like we asked our scientific committee to rank these teams from 4 until 9. I mean, after 3 teams, like the team of 4, 5, 6 until 9, and the team of Sklgp was selected for winning this prize, which they located based on their F score as the 5 team. So many thanks to our organizing committee. There are a lot of names that you cannot see here, but they are here. And yeah, many thanks to Professor Dr. Pedro Ramsey and all our other organizing committee. Also, our scientific committee was based, they are, some of them are really famous in natural hazards and landslides, Professor Qingsong and Martin Lusinger, and also AI solution. Okay, so, and yeah, here you can find our paper that is published, our landslide benchmark data set, which is globally, and we are very happy to continue this competition, not as a competition, but as a scientific challenge to increase the accuracy and solving the transferability problem in landslide detection. And I'm also really happy because we got very impressive solutions that I also didn't expect, such very nice solutions, that they are all based working on the data and also working on the models in artificial intelligence. So thank you very much. We are going to start with the third team, which are team Tanmlh from Technical University of Munich and DLR by Qingsong.
Hello everyone, I'm Qingsong from Technical University of Munich. And today I'm so excited and honored to share our work. The title is Towards Improving the Generalizability of the Semantic Segmentation Model for Landslide Detection. As we all know, this task is based on the Landslide4sense computation, whose goal is to detect the location and the extent of the landslide. And in terms of the data, we can see from this picture, the 12 bounds of the data from Qingsong and the 2 bounds of the slope and the DM are provided for us. The time period of this computation includes the validation phase and test phase, where 245 unnamed data and 800 unnamed data are provided respectively. In terms of our model, the motivation is the validation and test data sampled from different regions across the world may have spectral shares with the training data. That means different data sets will have different contributions. So we will consider the domain adaptation into our model. And the most factor of our model is that how to exploit the unnamed data and improve the generalizability of the model. So this is our motivations, and bear this our motivation in mind, our proposed our model. And this is the pipeline of our model, and the pipeline including 2 branches. And we can say this is the first branch is a teacher model. So what is teacher model? The teacher model first will trained on the labeled training data, and then we get a trained teacher model, and we will, based on it, we will obtain the pseudo label of unlabeled image based on uncertainty. So what is uncertainty and how to define it? We define it by the Monte Carlo dropout. Specifically, we will forward the data into this network for several times. And in each time, the first layer of the network will be random dropped out. And after several times, the variance of these times can be obtained. And based on this variance, we can obtain the uncertainty map. And after obtaining the uncertainty map, we will mask out the areas that the uncertainty is relatively high. And the remainder pixel will be considered as the landslide pixel. So this teacher model is to obtain the pseudo label. After obtaining the pseudo label, we will consider the second stage. This is a student model. This student model will train based on the labeled training data and the pseudo label of the unlabeled images. And the loss function is based on the cross-entropy loss and the Jaccard loss. So we will combine these losses to train the student model. And for the data augmentation, we also use some random flipping, crossing, and resizing to augment the dataset. And importantly, the mix-up operation is very effective in the whole training of our model. And for the post-processing, we use a dense conditional random field to post-process the final result. And for the implementation of our final model, as shown in this flow chart, we first step is the training dataset. So we use the labeled training dataset to training a model 1. And then the model 1 will be used, this is a teacher network. And then based on this teacher network, we will generate the pseudo label of unlabeled images. The validation is unlabeled images. And we will train two models, model 2 and model 3, based on this validation data. And the differences of these two models is that they have different architectures. And after the validation, we're going to the final model. We can say this model 3's architecture is similar with the final model's architecture. So we will use this model 3's weight to initialize the final model. And the model 2 is to generate the validation and test data's pseudo label. So based on the whole dataset, which including the labeled training data and the pseudo labels of validation and test data, which is generated by the model 2, and then we can get the final test result. And by doing this, we not only consider the labeled image and unlabeled images information, but also performed a kind of model ensembling in this by this framework. Okay, let me see some experiments. As shown in this table, this is on the test leaderboard result. And we compared with the model 2 and the final model. We can see the final model's performance is better than the model 2. So we can conclude that the ensemble modeling is effective for our final result. And we also do some application studies on the validation data. Okay, sorry. Yeah, we can compare the model 2 and the model 3 with model 1. We can say that the performance is better than the model 1. So the ensembling model is better and effective in our accuracy. And we can say we use the post-processing dense CRF, which is also benefit to improve the accuracy of the model. So this is the result. And we also have visualized some results. We can say this is uncertainty, this is prediction, this is dense RF. From first though, we can conclude that our proposed model can distinguish the road and the landslide, and also compared with these two counts, we can conclude that with the dense CRF can remove some inaccuracy areas, which is not the landslide. So next we will going to, this work is belong to our proposed perception and cognition machine learning for disasters. So what is this framework? Next, I will give the simplest introduction about this framework. I will give maybe 3 cases. The first case is based on the supervised semantic segmentation models. So for example, in terms of region, which is caused their original landslide, which is maybe caused by earthquake, and then we will make a training dataset to detect the regional landslide, and then we based on this training dataset and supervised model, we can detect the regional landslide quickly. So this is a perception for regional landslide. And then we come into the conclusion. Conclusion is that how to assessment the landslide. So we will consider the risk of every landslide and the loss of the landslide on the road, on the buildings, and other human activities. And this is a static cognition into this framework. And after the perception and the static cognition, we can finally assess the landslide in an end-to-end method. So we can also give some case is unsupervised. The first one case is supervised, and the second one is, for example, a new region, which is also called a regional landslide. And we will based on some domain adaptation with other unsupervised method to detect the landslide. So this is a perception result. And then we come into the conclusion. We add different static attributes to assessment the regional landslide in an end-to-end method. So this is maybe result. And the third case is that perception and dynamic cognition. We can say the one and the second case is the static cognition. What is dynamic cognition? For example, in this region, it's a disaster of diverse flow. And first, we will based on some supervised method. For example, our proposed improver to detect the landslide. And then the result of the landslide will be considered the initial condition of the neural simulation. So based on the initial result of the landslide, we can get the whole dynamic process of this region. So this is a perception and neural simulation, that is dynamic cognition to assessment the regional disaster. So I just gave some very simplest case and the simplest framework of our perception and cognition framework. And if you are interested in perception and cognition disasters, you can feel free to contact us, and maybe sincerely, maybe we can together to contribute to this community, and that is perception and cognition for disasters. Okay, thanks for your attention. Any question?
Thank you very much, Qingsong. Any question?
For your pseudo labels, did you use soft or hard labels?
We use a pseudo label, yeah, which is generated by the trained model, yeah. So and the uncertainty is maybe you can consider it an unsupervised method, yeah.
Your pseudo labels, like in the probability distribution of the prediction, do you use like the argmax or the?
We use variance of several runs to get the one uncertainty. And if we have this uncertainty, if it's high, we will mask out. If it's low, then this uncertainty we will give it a landslide region. Yeah.
Thank you.
Thank you.
May I have one question regarding your slide number 8? So anyway, my question is about dense conditional random field method, which is also really new, and we know that. And I'm wondering, like, how this very nice improvement happened with this post-processing process. Could you please tell us what it did?
Thanks for your question, Professor. And this then CRF you can consider operation based on some based in the computer version, which is that if this have a probability, if the result of this prediction maybe can have compared with the probability, and this probability is obtained by an unsupervised method, and based on this probability, we can post-process the inaccuracy region.
Thank you.
Okay, thank you.
Any other question? So if not, now we are going to give you.
Oh, that's nice.
Okay, the reason that we started from the third team is that because they are here physically, and we are sorry that still we have some restrictions regarding like COVID, and we don't have some team like physically here, but they will present their presentations virtually. So now we are going to second winner, the team SIG. That they used like Swin, and the rename is as SwinLS, adapting Swin transformer to landslide detection, which will be presented by Zhao.
Hello everyone, we are the Team SIG. Our team are honored to run the second place in the Landslide4sense competition. Our team members are all from the School of Artificial Intelligence, Xidian University in Chengdu. Next, I will introduce our proposal in this competition. The aim of this competition is to promote innovative algorithms for the automatic landslide detection using remote sensing images. Look at this picture at the left. They are from the competition homepage. We take them as an example. We need to detect the landslide area from the given spectral banks. Okay, I will introduce more details of the competition data. Basically, the data is mainly from Sentinel-2, which contains 12 banks, including RGB, SWR, NIR, and so on. Besides, POLASA and DM information are also provided. Look at the picture on the left. We visualize different spectral banks of the data. As a normal detection task, the category distribution of this dataset is extremely balanced. As shown in the red figure, I count the landslide and the non-landslide pixel ratios for the entire dataset. The pixel ratios of positive and negative samples is quite imbalanced. Next, I give some background knowledge of this task. The landslide detection task can be regarded as a binary semantic segmentation task. The authors who created the landslide benchmark treated many full convolution networks, also called FCN, as the baselines. We show the tables of the benchmark paper here. We can see that FCN-based segmentation model present good performance, achieving about 70% FE scores. Okay, based on this, I will introduce the motivation of this competition. In addition to the full convolution network, recently the vision transformer network performs well in semantic segmentation tasks. The key to achieve this is using self-attention mechanism. For example, the Swin transformer uses self-attention mechanism with shift window to capture the global relationships. After that, semantic expression can be obtained. So, we have a question that whether the landslide detection task needs self-attention mechanism. Okay, look at this picture. Virtually, the surface of the landslide area shows a similar response, which will provide true for model reasoning. So it's reasonable to focus the pixel relationship in landslide detection task. To verify this, we adopt the vision transformer model to landslide detection task. However, the result is not as good as we thought. Look at this table. It shows the performance of directly using Swin transformer for this task. It has a 6% of FE scores lower than the UNet model. So, how do we adapt the vision transformer model to detect the landslide? To take a closer look at what causes this, we use observation and experiments to better verify it. Look at the picture on the left. We found that the position of the landslide area in some multispectral doesn't match the landslide area of the ground truth. This makes us wonder whether the self-attention can still work when this useless spectral is dominant. Look at the dot for clarity. Then we perform a set of experiments. Okay, look at the picture on the right. This is a virtualization of Swin's feature activation map. From left to right, we gradually add RGB SWR near to the model and got this feature activation map. We can see that as some spectra which is not closely related to the landslide is added, the attention map gradually becomes poor. Okay, based on this, then we propose SwinLS for landslide detection using Swin transformer. SwinLS is a network with encoder and decoder structure. Look at this picture for clarity. Its encoder is composed of the base structure of Swin transformer, which has a powerful feature representation capability. Its decoder uses a convolution structure for decoding and fusing multi-level features. And then we make two major modifications. The first is that we select suitable spectral by a set of experiments. The second is that we propose a two-stage training method for the imbalance problem. The spectral selection experiments will be introduced later. Now, I'm going to introduce the second modification about balanced training. This stringency includes two stages. In the first stage, it uses weighted cross-entropy loss and novel loss to train the encoder and decoder. It helps the model to get a balanced feature representation. In the second stage, it uses cross-entropy loss to fine-tune the decoder to collect the bias of the classifier. After that, we add top lambda% high confidence pixels of test data to the training side and fine-tune the decoder again. Now we will introduce the experiments to show each part of this stringency. Table issues over experimental results of spectral selection. We tried multiple spectral conventions, and finally, the Swin transformer performed best when only RGB was input. By the way, we also found some dimension reduction method like PCA in in 5th line, but it not works. We think the operation lost the most important information of the landslide. Besides, we also traded some data transformation stringency for landslide detection approach. Data enhancement further improved the performance of Swin transformer. For the imbalance problem, we tried weighted cross-entropy loss, focal loss, novel loss, and the proposed two-stage training method. It shows that the balanced training further improves FE scores, which verifies the effectiveness of the proposed method. After that, Swin transformer is 6.2 percentage points higher than Unite. Finally, we show the experiments of self-training method. As mentioned before, we add the top lambda percent high confidence pixels of test data to the training data. Look at this picture. It shows how the lambda affect the pseudo label. Basically, if the lambda is larger, more pseudo label will be more pixel level pseudo label will be selected. Look at the table, we can see that how lambda affects the self-training results. We further show the visualization of the proposed stringency. From the figure, it shows that the stringency of each stage provides positive guidance of the model. Okay, next I will look ahead and summarize the work of the computation. In the computation, we found that some spectral is not suitable for self-flotation mechanism, and we select the spectral by hand, which was time-consuming and not adaptive. We have a rough idea now of using reinforcement learning to automatically select the spectral for Swin transformer. Second, we firmly believe that there will be better stringencies against the imbalance in landslide detection. In the end, we use a self-training method for semi-supervised learning, but it was very crude. We hope that there will be landslide-specific supervised learning method. Last but not least, our team is very grateful to the organizing committee, and our competition experiments is very good. Thank you very much.
Fantastic work, like it usually happens. Is there any question from audience here? If not, I just go through one question from your work. When you use like 14 all bands, you get, if I'm not wrong, you the best result with units, but not with your provided Swin method. And it was vice versa with the unit and Swin. Is there any explanation for that?
Okay. In my provided the paper, the full pages paper, I report my proposal in this way. And in the provided coding project, I also implied this idea. I think the report method is much with the code we provided.
Okay. Thank you very much. Thank you, Zhao. Now we are going to the first team who were Walker or cash prize of 5,000 euros from IARAI, and they ranked as the first team of Kingdrone. Progressive label refinement-based distribution adoption framework for landslide detection will be presented by Hengwei Zhao.
Hello, everyone. We are the RSID group from Wuhan University, and I will introduce our solution for the Landslide4sense contest, progressive label refinement-based distribution adaptation framework for landslide detection. This presentation includes 4 parts. The first part is the introduction. Landslide is a worldwide destructive natural phenomenon, bringing serious harm to society and the economy. Remote sensing technology offers the possibility of rapidly detecting globally distributed landslides. Landslide4sense competition focuses on landslide detection using globally distributed multi-source satellite imagery. And the Landslide4sense dataset provides an important resource for remote sensing and computer vision research on landslide detection. The Landslide4sense dataset has two characteristics. The first is that landslide has some small branches or itself is relatively small in area. And the second is landslides are distributed globally. These characteristics present great challenges to landslide detection from remote sensing imagery. The first challenge is small objects and class imbalance. The landslide will have some small branches or landslide itself is relatively small in area. And as a result, there will be a serious imbalance in the number of pixels between the landslide and the background. And as shown in this figure, where the number of pixels in the background is 49 times that of landslide in the training dataset, and the small objects and class imbalance will lead to lower recall. The second challenge is the distribution inconsistencies. The mean and standard deviation values of the training, validation, and testing dataset are counted band by band and displayed in this figure. And the histogram is the mean and the error bars are the standard deviation. And because the landslide remote sensing imagery were collected from all over the world, and there is a significant inconsistency in the mean and standard deviation values of the training and the validation or testing sets. The second part is our proposed framework. This is the flowchart of our proposed framework. And this framework includes processing, model ensemble, training and inferences, and label refinement. Skill promotion, loss, and OHEM are used to solve the problem of small objects and class imbalance and to boost the recall. Skill promotion is performed in the data processing stage, and the original image is scaled up from 128 to 512. And in the learning stage, LU-based loss was considered. And only pixels in the top 70% of loss values were considered in the optimization. Separated normalization and label refinement are used to solve the problem of distribution inconsistencies and to align the statistics of the training and the testing data. Separated normalization is proposed to reduce the difference between two domains, which use different mean and standard deviation to normalize the data in the source and the target domains. And the mean and the standard deviation values were calculated from training and validation or testing data respectively. To further reduce this difference, progressive label refinement were proposed to improve the pseudo labels. And based on the model prediction, the pseudo labels were generated from models using threshold of 0.7. And as for the next round, the model will be trained by the training samples and the test image with pseudo labels. Different advanced deep learning architectures are selected to boost the overall performance. In our framework, Swin transformer and the efficient net V2 are used as our backbone. And the U decoder was used as decoder to refine the spatial details. And the batch normalization is replaced by cross-sensor normalization in all models to increase the generalization ability. And the Segformer also be used in our framework, and the Segformer uses MLP as decoder to refine the spatial details. All components make up our proposed framework, and the model updating and the label refinement are performed interactively. The third part is the experiment. Landslide4sense dataset is collected from diverse regions and diverse geographical regions present great challenges to landslide detection from remote sensing imagery. And this is the result of the validation leaderboard. And as shown in this figure, the method to solve the problem of distribution inconsistencies play an important role. Both separating normalization and the progressive label refinement improve the F1 significantly. And the method to solve the cloud imbalance and the small objects are also effective. This is the result of the test leaderboard, and as shown in this figure, the F1 soccer of the best one model in the validation leaderboard is 33.07, and the performance of the model are progressively improved as the pseudo labels are iterated. Last is the conclusion. In this presentation, we introduce the characteristics of the Landslide4sense dataset, and we analyze challenges based on these characteristics, and based on this analysis, we proposed the progressive label refinement-based distribution adaptation framework for landslide detection. And in the future, we will focus on multi-temporal landslide monitoring. This is our references, and that's all. Thank you.
Thank you for your very nice presentation. Personally, I really like your methodology, and you really deserve to be the first ranked and as the main winner of our competition. Is there any question from you, please?
Okay, so maybe just one quick question. As in your slides, you mentioned that you use many different architectures, like including the Swin transformer and different models as base network to do the landslide detection. So my question is, how will you process with these different results from different architectures in the ensemble learning?
This is Jimmy from my university, and I will answer this question. You just see that we use different architectures such as transformer, Swin transformer, and efficient net. And we train these architectures individually in each round, and we ensemble these architectures outputs with mean function. And this we can see that the ensemble result can significantly improve its performance. And in the next round, we train these architectures individually again. So this is our process.
Yeah, it's a very nice work, and I wonder that how to obtain the pseudo label in your proposed model and how to refinement of it.
Oh yeah, the pseudo label model is we use a threshold to use the pseudo labels, and we set the threshold is 0.7, and only the prediction possibility about the 0.7, and we use it as landslide label.
Okay, thank you for your very nice presentation. Now it's the time we shift to the winner of our special prize for creative and innovative solutions, AI solutions for landslide detection. The winner team is Sklgp, which they selected based on ranking of our scientific committee. And multispectral unit for landslide detection will be presented by Lin Bai from Chengdu University of Technology.
Our team have the special prize for creative and innovation solution. Firstly, we resign for the organizing committee. Let's start. This slide including five parts. Affiliation in the first parts. before we get the computation, our team comes from the Sklgp, the state key laboratory of geohazard prevention and geo-environment protection, and Chengdu University of Technology. And so actually we did a lot of work related in this field. So in the Landslide4sense computation dataset, we noticed that this is a big dataset and which contain the landslide in the 4 areas in the world. So and it's multispectral. So when we get to the dataset, we just consider 2 questions. The first is that for the landslide detection, when we use the deep learning model in this field, it's very difficult to detect it because it's complex morphology of landslide. And so usually the detection accuracy is low. And the second question is that in this computation data set, the date formats is different for the original formats. It's have 14 bands, and in the original we just use the RGB bands for the detection. So in the very beginning, we just tried a very simple way, just similar with the baseline in the GitHub of the committee, and we just feed all the 14 bands into the model, and we compare with 3 models in there, the units and the deep label V3 and the deep label V3 plus, and we find that deep label V3 plus is actually the best model in there. So so in the last step, we just focused on the dataset itself. We found some information in the internet that it's in the Sentinel-2, which is the satellite of the provide the data for the non-state for competition. We noticed that the 14 bands, the 12 bands in this state has different ratios, resolutions. Around the organization and just propose it to the same resolution to the same resolution. And we just think about that maybe there are some influence for the model performance. So when we redesign our model, we just pay more attention to this aspect. This is our model structures, and we can see that the most parts of our model is simply the model below the picture, and that's the basic unit model is our baseline model, and in the upper of the picture, it's another branch which we used to extract the some more information from the higher resolution data bands. This new branch is very simple. It's just have 4 and 3 layers, 4 layers. And when the B2 and we see the band 2 and B2 and after is that B2, B3 and B4, B8, which has the high resolution data and to 2 convolution layer first day and then to a SE layer blocks, and then the output will be simply connected with the concate with the feature in the baseline, the unit feature, and then the fusion feature will be used for the final detection. And so this is the experiment our our experiment, all the method is simply with 8 batch size and 8 optimizer cosine learning rate, with warm up and the basic nodes cross empty nodes and only 200 epochs. So when we getting the computation, we split the first dataset into 2 parts, and 1 part for the training and 1 part for the test. So in the next step, we compared 5 models in the validation dataset, and we can see that the operation of our dataset and the unit, the multispectral unit we call have the highest recall and only a slight decrease in the oppression compared with the unit, and the final F1 score is the highest, and with 77.83. And then we choose 3 examples, and that's our model deep predictions. The first example is this. We can find the detection maps of the stream model are similar, but the maps of deep level V3 are more complex, and so this is maybe the deep level V3 have the most complex structure, and so it can get more information about the non-snake margin. And the second example is that although the morphology cannot be seen from the RGB image, the stream model can detect the non-state, and this means that the other bands instead of the RGB bands can also contribute to the final result. So in this example, we can see that the multispectral unit works better. Final example is that 3 models have similar detection effects, but in the small non-state, we can see that our model have the better performance. So the conclusion, and the first is that we introduced a new model called the multispectral unit, based on the traditional unit. And the second is that unit branch extra features from the whole 14 bands, while the inverted residues and the minor bottleneck pay attention to 10 meters pixel bands. The feature from the 2 bands will be fused in the end. The third is that the experiment shows that this kind of a structure can get a better performance than the traditional unit. That's all. Thank you.
Thank you very much, Lin Bai. Okay, multispectral unit. Is there any question from audience?
I have a question. Can you hear me?
Yes, please.
Yes, it's a nice work, and I'm concerned about your abbreviation of SN. SN in your architecture, what is the function? Can you answer it?
Could you expand what function in this model, in our model? Our model is consistent with 2 parts. One part is just the basic unit, and another part is a structure like the SE block, which means to extract the features from the more Persian resolution bands, and then the feature will be directly fused with the feature of the units in the final, and then this function and in this function the function in this stage is simple concate. We just fuse the 2 feature directly.
Thank you. And another question is, you used bands from 1 to 14, but the upper you use only 3 bands. Why you divide these bands to 2 groups? Are you refer to their resolutions?
The upper band is actually the 4 band, and in this slide, we can see that those 4 bands all have the highest resolution, and this we can see the dates in the Landslide4sense dataset, and it's from the Sentinel-2, so we can get the information in the Sentinel-2 websites, and this is the data we get, and all the bands in the 10 pixel meters used in the upper branch.
Lin, but actually we also provide this this information in the website, in the competition website. Okay. Any other question from? So very great idea, like multispectral unit. Have you ever used it for any other remote sensing application except landslide detection or any other like multispectral image?
Actually, no. And this method is just we just consider it.
This is the first time.
Yeah, this is the first time, and we will find this in the future more.
Yeah, yes, we have tried, but the time is limited. So we don't use the extra images.
So very nice. I'm very happy it was the first using of this method, and it was successful for our task of landslide detection from Sentinel-2 and ALUS Placer. Thank you. This is all from this season. Thank you for all presenters and audience.